Okay, looks like the rush of folks coming in has paused a little bit. So why don't we go ahead and get started so that we can try to keep to our schedule. My name is Ben Runkle. I'm from the University of Arkansas. I'm happy to be the host or moderator of this plenary session called Informing Decision Makers. So thank you all for helping us think about what are the steps between science and action. And we have four great speakers I'm excited to hear from today. The first one is Gyami Shrestha, who's from our US Carbon Cycle Science Program Office, National Coordination Office. She's responsible for research, coordination, documentation, and dissemination of the Carbon Program Office and the Carbon Cycle Interagency Working Group activities along connecting the science community at federal agencies and also to university and other researchers. She led the charge on the state of the climate carbon cycle too, sorry, Gyami, challenging acronym. She also has a research background in biochar and black carbon with an emphasis on prescribed fire, which must have been an interesting last couple of months for you to think about in that perspective. So we're looking forward to your talk on past to future, a vision for diverse and inclusive carbon cycle science collaborations. Gyami has also told me that she'll be using a website called Slido for 3 live polls. The code is AmeriFlux. I'll put that into the chat. So go ahead, Gyami, the floor is yours. And I'm not hearing you. And we also don't see your slides. Sorry, gang. Can I unmute you? You don't look mute from my side. Yeah, so just a moment.
Gyami, you are not muted.
I got it. I think I need a hand from Kristen or one of the moderators. If you go to the phone that starts.
You can hear me now.
There we go. Yeah.
Yes. All right. All right. Wait. Hi, everyone. How is everyone doing?
Good.
All right. So you can see the screen?
Yeah.
Okay. All right. So first, I'd like to thank all of you, and especially the planning committee, for inviting me. It's an honor, of course, to speak with all of you. And again, greetings, hola, bonjour, namaste, any language that you speak. My name is Gyami Shrestha, and I'm speaking with you from the Washington, D.C. area, which is the ancestral home of the Anacostans, Nakochag, Piscataway, Tamung, Kay, Nentengo, Mataponi, Chikahomini, Monahon, and Powhatan peoples. So I come from a culture that really reveres its ancestors and the past sacrifices that have made our present possible. It is in this spirit that I will focus this talk on the history of interagency carbon cycle science collaborations in the US and how it can inform a future vision for a more diverse and inclusive collaborative future. And first, a disclaimer. The thoughts I will be expressing here are my own and do not represent the opinions of any agency or federal body, unless otherwise stated. So as Ben mentioned, I will be posing some abrupt, surprising questions in between my slides, so be ready. If you have a secondary device or phone, go to slido.com, enter the code AmeriFlux, and only the first few answers will be displayed and all the responses are anonymous. And I really want to know what all of you are thinking while I'm talking, so be ready. So during this talk, I'll talk about the history of interagency carbon cycle science and some recent programmatic developments from the carbon program, big ideas, some talk or two slides will be shown, and also I'll wrap up with our or your vision for a truly diverse and inclusive carbon cycle science collaborative future. So a not so brief history of US interagency carbon cycle science. The early years. So the next few slides incorporate some extracts from a manuscript that I've been working on for quite a few years now, and hopefully will be published soon. And I'd like to acknowledge the input of some of you maybe who are in the audience. Some of you have already seen some versions of this manuscript, so thanks for your input. So in 1965, President Lyndon B. Johnson was the first US president to address the carbon cycle in the US as a steady increase in carbon dioxide from the burning of fossil fuels, altering the atmospheric composition in a global scale. The President's Science Advisory Committee, in fact, released a report called Restoring the Quality of Our Environment, with a chapter on atmospheric CO2, concluding that fossil fuels were the only recent significant source of carbon dioxide added to the atmosphere, to the ocean atmosphere biosphere system. One of the earliest workshops by the US government was organized in 1977 on this topic, on the global effects of carbon dioxide from fossil fuels, many years after 1965. In 1978, the first US National Climate Program was established by Congress. Subsequently, DOE was the lead agency for a study on carbon dioxide and climate, along with other agencies and departments, namely State Department, NASA, NOAA, USDA, EPA, NSF, and USGS, leading to basic research, impact assessments, observation techniques development, so on and so forth. DOE, and after that, in 1970, the Carbon Dioxide and Climate Program was established within DOE with the goal of predicting the environmental, social, and economic costs of increasing atmospheric concentrations of carbon dioxide. The following year, following a request from the White House Office of Science and Technology Policy, an ad hoc study group on carbon dioxide and climate produced a scientific assessment of CO2 and climate. In 1990, the USGCRP, or the US Global Change Research Program, was then codified in the Global Change Research Act of 1990, which I'll talk about a bit later. Between 1995 and 1998, an interagency working group outside of the USGCRP called the Terrestrial Ecology and Global Change Research Program, TECO, released 4 interagency research calls totaling up to $8 million each year. And a third of that funding was awarded to carbon cycle science research. In 1998, the community, the science community, so at the grassroots level, requested better coordination of carbon cycle science research in the US. And the National Research Council subsequently released a special report called the Global Environmental Change Research Pathways for the Next Decade, focusing on a comprehensive carbon cycle science research strategy. In 1998, the Carbon Cycle Interagency Working Group was formally established under USGCRP auspices as a new iteration from TECO that we consider our predecessor. In 1999, another grassroots effort led to the development of a 1999 US Carbon Science Plan. So the first US Carbon Cycle Science Plan, really, which was led by Jorge Sarmiento and Steve Wolfsey. And the Carbon Cycle Interagency funded that effort. In 1999, the US Carbon Cycle Science Program was formally established under USGCRP auspices, following recommendations from the US Carbon Cycle Science Plan. In 2001, the National Research Council organized a workshop funded and sponsored by the Carbon Cycle Interagency Working Group, focused on bridging social and natural sciences in carbon cycle research as a first attempt to produce the needed understanding of the carbon cycle that could inform public decisions. In 2001, a global carbon cycle initiative was started, which was sort of envisioned by the Carbon Cycle Interagency group, and established a strong foundation, a stronger scientific foundation to develop the North American Carbon Program, and also to originate the idea of producing the first state of the carbon cycle report. So this is an attempt, work in progress, to sort of like illustrate these early developments in interagency coordinated carbon cycle science in the US. And I tried these different ways, but it's still a work in progress. But as you see, it makes more sense if you start from the end, where the Ocean Carbon and Biogeochemistry Program was sort of established in 2006, and NACP 2002, US Carbon Program 1999, CCIWG, and then you work backwards, but it is still a work in progress. In 2002, NACP was established. In 2003, 2004, further foundations for the development of the first state of the carbon cycle report were established, and investments. A new initiative called the Climate Change Research Initiative sort of led to more investments, prioritizing science to evaluate the knowledge of carbon cycle dynamics relevant to the impacts of the US on the US and contributions from it, and also US decision support for carbon management and policy. An expansion of the AmeriFlux network to measure net terrestrial carbon dioxide, and the development of innovative modeling frameworks was also prioritized at that time. The implementation of the North American Carbon Program and the Ocean Carbon and Climate Change plans was also emphasized by committing to establish program coordination and data management infrastructure for new research opportunities. 2004, a government-level partnership, CARBO-NA, was established among Canada, Mexico, and the US. OCB, the Ocean Carbon and Biogeochemistry Program, was established in 2006. Scott Denning et al. Developed the first NACP science implementation strategy. The first SOCR was produced and published, led by Tony King and Lisa Dilling. There were a number of intensives. One of them in 2007 was the NACP Mid-Continental Initiative. In 2011, the first US Carbon Science Plan was published, and in 2012, the USGCRP Decadal Strategic Plan was released. Now, just to make sure you're paying attention, here's my question. Consider your past and current collaborations. In this context, what are the main constraints other than funding? So please go to slido.com and enter AmeriFlux. And we'll spend maybe 30 seconds on this. And if everything works, then your anonymous responses should appear on the screen. Physical distance, security, more, okay, metadata, okay, integration, so, okay, personal interact, different disciplinary traditions, time, yes, training, 3-year time limit of contracts, yeah. Siloing, security, organization, unclear unmet data requirements, collaboration, privacy, power supply, access, spatial heterogeneity, lack of model experiment coordination, relationships, Okay, maybe 10 more seconds, so enter your responses. I'd love to know more about your constraints. Access, networking. Don't be shy. This is your chance to express yourself. Okay, 5 more seconds. Okay, then let's move on. Thank you for your response. This is really useful. Time, security. Right. Intercomparability. Thanks. Okay, let's move on. Okay, let's talk more about the present. First, the USGCRP, the US Global Change Research Program. The USGCRP began as a presidential initiative in 1989. It is mandated by Congress by the Global Change Research Act of 1990, and it now comprises 13 agencies with responsibilities in global change research. So the mandate is a comprehensive and integrated US research program will assist the nation and the world to understand, assess, predict, and respond to human and human-induced natural processes of global change. Through the USGCRP, member agencies work to coordinate and advance global change research across the government. They deliver products mandated by the Global Change Research Act, such as the National Climate Assessment and the Decadal Strategic Plan. The USGCRP does not independently set agency budgets or issue funding calls. It does not conduct primary research, and it does not develop federal policy. To avoid the bust and boom cycles of producing national climate assessments, in recent years, the USGCRP has produced a number of special reports. One of them is the second state of the carbon cycle report, or SOCR 2, focused on the carbon cycle, which was led by the US Carbon Cycle Science Program, which itself is led by the Carbon Cycle Interagency Working Group. So here we are, shiny, happy people, the US Carbon Cycle Science Program folks. So on the left, this is one of our last in-person meetings in 2019, where most of everyone was there. And a special tribute to Dr. Ken Mooney from NOAA, who passed away in August. He's there in the bright shirt on the left, next to Mike Falkowski. And on the right is the first and last joint meeting of the Carbon Cycle Science Steering Group, which we don't have anymore. It's a long story. And also the North American Carbon Program Science Leadership Group in 2013. So we operate under the USGCRP auspices, and we also have many activities of the science community, namely the North American Carbon Program, the Ocean Carbon and Biogeochemistry Program, and also international partnerships such as the Global Carbon Project and CarboNA. Our mission is to coordinate and facilitate federally funded carbon cycle research and provide leadership to the US Global Change Research Program on carbon cycle science priorities. We mainly promote interagency cooperation and coordination. We involve the science community in providing the needed science to understand the carbon cycle, to help secure funding and prepare individual and joint agency initiatives. And we're also instrumental in the process of prioritization of US government cycle science research streams. So some key products and outcomes, which only represent the tip of the iceberg from the program. So much of our work is informed currently, or has been informed, by the 2011 US Carbon Cycle Science Plan, which sort of informed many of the big ideas that we've worked on the last few years, including urban and human carbon interactions, coastal, blue carbon activities, carbon observations, region carbon assessment, so on and so forth, which we sponsored via multiple workshops and also multiple publications, including SOCR 2, which you see. So these are the headlines from some of the publications that came out of much of the work, much of the workshops that we sponsored the last few years. And these all informed the second state of the carbon cycle report, as well as many agency and interagency activities in the last few years. The scientific framing for SOCR 2 was based on the 2011 US Carbon Cycle Science Plan, and I will not go through all of those, but that is the basis for all of that. And this is more on soccer too. We reviewed over 3,764 publications, and we've worked over 200 with over 200 experts across 3 countries. And as you see, I think we're almost. I have like how much time? 2 minutes? 5 minutes? Okay. So this is an effort at analytics. Socrates has been viewed from over 5,000 cities in the world, so pretty good. I will not go over through all this because I do want to talk about. There's so much more to do. Go to carbon2018.globalchange.gov. Go to YouTube, search for US Carbon Cyber Science Program webinars. There are 16 webinars that are uploaded. There is a science implementation plan of the NACP that's in the works, so keep an eye out for that. I have a few more slides, but I do want an answer on this. What do you think is the future of carbon cycle collaboration? Any new opportunities we can tackle or improve? 30 seconds, you can provide quick answers. And then I have a few more slides, Ben, if that's okay with you, because we started late. All right, go to slido.com, enter AmeriFlux, and I just want a few words on what can we improve? What are the new opportunities we can tackle or improve? Multi-source observations. Also, nitrogen, water. Okay, integration between scales, sharing data. Okay, cross-network collaboration, integration between scales. 10 more seconds for your answers. Natural climate solutions, okay. Resolving uncertainty. Carbon management, involves stakeholders. 5 more seconds. Hurry up. Okay. Paired sites, okay. All right, all right. Community modeling. All right, let's move on to the next slide. Thanks, but you can keep on sending your answers if you'd like. All right. So a note on diversity, inclusivity, equity. So this was our soccer team, most of it anyways. And you see we're really diverse. We're really happy at that time. We had conducted a survey back then. And you see like we had a good mix, you know, male, female, okay, 40%, 60%, and then senior level, mid-career level, yes. But we forgot to include race in our survey. We did not collect racial or ethnic data. We did not collect disability data. We failed in that respect, and we really need to better integrate, you know, our indigenous, our black colleagues, and our people of colors. We need to do better, and they need to be represented in these highly influential scientific assessments to really represent who we are as a scientific community and who we want to be. June 16, 2020. NACP released a statement on anti-racism, and many of you signed it. Thank you. We listed a number of action items back then. We need to work on them. Particularly, you can go to the NACP website or carbonscience.us. Dr. Asmeret Bere a few days ago released a couple of blog posts on amplifying Black voices on Springer Nature, and it's heartbreaking reading her experiences. So let's all think, when you see somebody who does not look like you, think about what they may have gone through to reach the level they're at. And we all need to do that and consider that in our work and collaborations. And these are some nice graphics, and I thought the FluxNet courses are amazing. This picture, look at how diverse it is, and just kudos to everyone. And you know, this graphic about what equality versus equity explains so much. And also a recent tweet from Ben Porter on this new methane flux data, which, you know, data from everywhere, all around the world. And it's just amazing, like, you know, the diversity in the sciences, diversity in the data, and it's just a need to acknowledge everyone, and, you know, everyone from where we're collecting the data, who we're working with around the world, and so on and so forth. So if there's still time, this is the last question, and then I'll wrap up.
Yeah, maybe.
Me, Ben? Yeah.
Yeah, good. I think we can answer this, and then I think we need to move on to the next speaker.
Okay.
So we have a full.
So, what is your vision of a diverse and inclusive carbon cycle science future collaboration? What can we do better? 20 seconds since Ben's being very forceful. Please answer this question. If you have a vision, what can we do better? What's in the future? No answers? Okay, stand up to microaggressions. Yes, thank you. Start early with high schools, yes. Incorporate tribal leaders, yes. More accommodation, more management, education and training, fund travel and opportunities, co-author inciting scientists outside the US, and by POC, yes. Diversity and leadership, codes of conduct for field work. All right, 5 more seconds. Education and training. Yes, let's move on. Ben's getting anxious. Thank you so much, and keep on sending me answers. You can email me. I got this fortune cookie here like last week. I hear and I forget, I see and I remember, I do and I understand. So let's all work on this. Future is exciting. And here's my contact information. So you can email me your answers anytime. Thank you so much.
That's great. Thank you very much, Gyami. I wonder if people can give a little virtual round of applause there. Appreciate all of your different insights and encouragement and inducement to do and to understand. So thank you. I hope that you'll be around virtually in the gather space the next days, and people can find Gyami and network with her and discuss follow-up to this talk. So we should move along. Thank you again, Gyami. I wonder if you can release your slides, and then we have Patty Oikawa will give the next talk. Patty's a professor at CSU East Bay, Department of Earth and Environmental Sciences. She does research at the interface of land management practice and environmental science, looking at how to manage greenhouse gas emissions and other trace gases to minimize the effect of the landscape on the air and atmosphere. So she has a PhD at Virginia and postdocs at Riverside and Berkeley, and she'll present today on the topic of flux measurements and modeling to inform carbon markets and climate change mitigation. So go ahead, Patty.
Oh, thanks, Ben, for the introduction. Thanks for having me. And thanks, Gyami, for the great first talk. I missed that the blog post by Asmer. I'm definitely going to check that out. So let's see if I can get my screen share going here.
All good.
Joke. All good? Okay, great. Thanks, Ben. Okay, so yeah, so I'm going to talk today about using flux measurements to help inform climate mitigation and carbon markets. This is all, inspired by our desperate need to have some negative emissions here. You're all probably familiar with this image. This is an image that's scaled down to the state of California. And our need in California to reach our goal of neutrality by 2045 is going to require substantial negative emissions. So there's a lot of interest in my state where I work and live in California to kind of develop some of these strategies, particularly storing carbon on land. And in my lab, we're right now really focused on wetland restoration, as well as compost amendments to rangelands. So I'll talk about both of those projects today. Okay, so the first kind of like the roadmap for this type of research is to use flux data, both eddy covariance and chamber flux measurements, to help develop models and get better predictions of carbon storage in soils and also methane budgets. And use those models to identify uncertainty and data gaps. And then what I really want to highlight today too, especially for this session, is how we can better use our eddy covariance data and to produce tools for these communities. Okay, so I'll kind of break this into the two sections by ecosystem type. So start with the wetland work, connecting those measurements with carbon markets in California and a modeling tool that we're developing right now, and then move on to rangelands and how we're connecting that soil amendment work with stakeholders in tribal communities across California. Okay, so this work all started when I joined Dennis Baldaki's lab at Berkeley, and in his lab I worked on developing this peppermint model. And it's a very simple process-based model that was informed using this little meso network of towers that Dennis manages in his lab. And we used a Bayesian hierarchical modeling approach to parameterize the model and characterize uncertainty. We left one of the sites out as a complete independent validation site for the model. And these are in restored freshwater peatland ecosystems. So there's quite a bit of methane coming out of these systems. There's an image of one of the wetlands right here. So getting a model that could help us characterize and also provide rigorous estimates of uncertainty around methane budgets in these systems is particularly important because methane emissions are so high. We also worked on developing and expanding this model to rice paddies as well in California. California grows a lot of rice, and particularly applied it to scenarios where they were experimenting with water table and alternate wetting and drying in rice systems, which Ben knows a lot about. So we brought this model into and wrote it into a carbon offset protocol, which I co-authored with some collaborators, such as Steve Deverell at HydroFocus. And that protocol kind of outlines all the steps in which you would develop a wetland and then constrain the greenhouse gases exchange in that ecosystem and then get carbon credits for that restoration process. And so the American Carbon Registry approved the protocol, and they're the ones that oversee all of the carbon credits for California's cap and trade system. And it was first used this past spring in 2020. So the California Department of Water Resources actually used the protocol for the first time, and they had a wetland restoration project of 1,700 acres. They received about $62 per acre. We're expecting this number to go up in the future as this becomes moves into the compliance market. Right now, it's in the only operating in the voluntary carbon market. I'm happy to answer more questions about this later on if you guys have them. And then I've just heard recently there's lots of more projects in the pipeline. So not just wetlands, but also rice conversion in the Delta and potentially thousands of acres using this. So this was a really great example of how you can directly link eddy covariance measurements and with models and use that to help us inform carbon markets. So that's been very productive. One thing that kind of came out of that process was identifying some of the weaknesses. So there is a huge data gap for this system in California, which is tidally influenced wetlands. And so in my lab, what I've been doing is kind of pivoting and working a lot more in this sphere. And these are really interesting systems because they have complex carbon cycling with both the atmospheric exchange of CO2 and methane, carbon burial, and then the lateral exchange of dissolved inorganic and organic forms of carbon. And methane emissions from these tidally influenced wetlands is a large source of uncertainty in these national greenhouse gas inventories. So there's definitely data needs in these systems. So I started a project a couple of years ago now with a group of researchers here, and we have a couple of sites that we're managing in the Bay Area. One that's managed by my lab, it's a salt marsh, and Lisa Marie Wyndham Myers is managing this other brackish tidal marsh called Rush Ranch. These are both AmeriFlux sites. And what we're doing is we have the towers to characterize the atmospheric exchange, and then we also have at both sites lateral carbon flux stations that are taking continuous measurements of lateral exchange of dissolved CO2 and organic carbon, particulate carbon. And they have a constrained now 1-year budget of the entire net ecosystem carbon balance in Rush Ranch, and found that about half of the CO2 that's taken up as measured by the tower is lost laterally. And we think the similar things are going on at Eden Landing. These are the carbon budgets from a few years of Eden Landing and Rush Ranch. So we're really excited to see and help use these continuous data sets, very temporally rich data, to help us better understand the carbon balance of these systems, and also use that to build out models that can predict those lateral fluxes. I also wanted to highlight that these ecosystems, are in stark contrast to the freshwater peatlands I mentioned earlier. They have very, very small methane budgets, and which makes them a little bit easier to operate in the carbon market community. The mitigation potential is a little stronger, and the radiative forcing is a little more straightforward and immediate. But the other kind of drawback to these low methane fluxes is that towers aren't so good at constraining really small methane fluxes, especially the open path sensors that we've been using. So we're helping to better flesh out the details of those methane exchange measurements with chamber work. And a graduate student of mine, Julie Shahan, is presenting a poster tomorrow morning, and I encourage you to go see her poster, hear more about that. This also kind of led into the methane working group under the Coastal Carbon Research Coordination Network, which is also a group that's very focused on connecting flux data with stakeholders. And I'm co-leading up this methane group with Ariana Arias-Ortiz at UC Berkeley. And what we're working on right now is bringing together methane flux data from all coastal wetlands in the United States. And this is going to including both chamber and eddy flux data. And we're working on making this a very curated open source data set. And then using that data to inform and develop models. One we're working on right now is the MEM peppermint model. So we're bridging this marsh equilibrium model with the peppermint model. The MEM model is really good at predicting soil accretion and carbon burial in these tidally influenced wetlands, and predicting also tidal collapse in the future and with sea level rise. And then the peppermint is now getting tied to that model to give us rigorous estimates of methane at the daily time step. And then we're bringing all that modeling product into an open source modeling tool GUI format. And so this is really exciting. This is work being pioneered by a graduate student of mine, Michael Naharo, and software engineer Nabil Chek. And they're working on bringing that model in and hosting it through the Google Earth Engine platform. So users can type in the coordinates of their wetland and give us some information about the site. And then they can run MEM peppermint in this GUI and get outputs of greenhouse gas budgets, soil accretion, and also really importantly, uncertainty in their estimates. And so again, this is all being informed with this Bayesian hierarchical modeling framework. And just want to emphasize, particularly with carbon markets, the more uncertain your budget is, the less offsets you receive. So this is an important part. Also, particularly with methane budgets, it can really be the difference between positive and negative radiative forcing. Okay, so then I'll just use my last few minutes to talk about the rangeland work. And this is part of the Working Lands Innovation Center. It's a consortium of scientists across California. It's a big group here. And we're testing different types of soil amendments across managed ecosystems in California, row crops and rangelands, and looking at compost, biochar, rock amendments, and also combinations of those, and looking at how those can help enhance soil sequestration as well as reduce N2O emissions. So we have over 100 acres of land in demonstration, 27 sites, monitoring and tracking carbon deep down up to a meter, and then using that to inform models and connect with commercialization efforts and other stakeholders. So our role in the project is we have a new eddy covariance, new AmeriFlux site that has a year of data now in a rangeland, and we're applying compost to 5 acres of the footprint next week. very exciting. And then part of the footprint is going to be left as a control area and look at, it's really exciting because this is the first time we're looking at the compost amendment process at a very large scale beyond chambers and integrating across large spatial surface, and also characterizing how this is affecting water cycling, which can be a really important impact of the compost amendments, is in changing soil water holding capacity and climate resiliency. So our first year of data is here. It's just showing it's a very carbon neutral ecosystem. And Isabel Torres and Tommy Fenster are graduate students in my lab working on that project. One of the really exciting things about this is connecting this with potential users of this type of data. So one example of this is we're working with the Palma tribe in San Diego. They have over 6,000 acres of land under management and are very interested in applying some of these techniques and data to improve sustainable land management. Also, they're very interested in fire resiliency and changing soil water holding capacity on their land. So I think out of this, it's very exciting to be passing these data along and bringing it and providing it in tools, modeling tools, what have you, in a way that other people can really benefit from this type of these measurements and participate in carbon markets and get some kind of financial support for sustainable land management. Okay, so with that, I'll just thank my sponsors here and all the students in my lab and my collaborators. Thanks.
Sure. Thank you, Patty. Very nice talk. I wonder if there's any quick questions. If not, maybe I'll sneak in one and ask if there's any expected albedo changes with the compost addition to the soil that could also play a
Yeah,
role.
I mean, I definitely think that's going to be part of the story because, I mean, especially right now, it's late, it's fire season, everything's super dry and the grass is all dried out and blonde, and we're going to be applying this very dark compost. So it's going to be definitely changed albedo. And that's another thing that hasn't really been investigated with these types of amendments. Once you start scaling them up, there's going to be other ramifications and changes that we haven't really accounted for to date using just like chambers and smaller plot type studies.
Okay, very good. Good, yeah, some encouraging words also. Oh, Stephen asks, what is the timeline for Google Earth Engine?
Oh yeah, so that
Cool.
is in development right now. So we're hoping it'll be done within the next year or so. So 6 months to a year.
Good, push.
Yeah.
Cool, well, we should move on to Forrest's talk. Thank you again, Patty. Forrest, if you're there and able to unmute and share your screen, that would be great. So Forrest will present on OpenET and applications of AmeriFlux for water management. And he joins us from the NASA Ames Research Center with expertise in remote sensing. He's also affiliated with CSU Monterey Bay. So staying on the West Coast there.
Thanks, Ben. Can you hear me all right?
Hear you, see you good. Thank you.
Perfect. Great. Thanks. So really happy to be here on behalf of the OpenET team today. What I'd like to do is tell you a little bit about OpenET, talk about some of the applications we're developing to support water management and agricultural production in the West. And then also talk about the role that AmeriFlux data is playing in this effort and why it's so central to our ability to develop operational applications of evapotranspiration data. And OpenET is really a community-driven effort that involves over 40 scientists and software engineers from 3 federal agencies, 6 universities, Environmental Defense Fund, Google Earth Engine, and Habitat 7, a web development firm that specializes in visualization of large scientific data sets. Really been a fun project to be a part of and to have the chance to come together as a community, leverage over 3 decades of research, and start to learn from each other to develop an operational system for mapping evapotranspiration at field scales for the Western US at daily, monthly, and annual time steps. The current alpha version that's out for testing with partners right now It includes data for 11 states. We're looking at about a couple million fields, 4 billion data points. By the time we're done, we'll have about 100 billion data points in the system. We're currently adding data for the Dakotas through Texas. So by the time we launch next year, information will be available for the 17 Western states. And we can go back as, basically for the full Landsat data record back to 1984. The system provides information both summarized for individual fields as well as the wall-to-wall gridded satellite data products at the original Landsat resolution of 30 meters by 30 meters, or about quarter acre per pixel. As we zoom into individual fields, simply by moving the cursor over a field, annual ET, the monthly time series for the year selected, and information about the field is displayed to the user. And then by clicking on a field, you can retrieve the monthly and assume the daily time series for that location or for any pixel or location across the Western US. Information is available as an ensemble value calculated from the ensemble of methods being implemented by OpenET. So we're looking at the monthly ensemble value here. Users can also retrieve data from individual methods in case they've been working with one or more of these models or approaches in the past, and also to provide an estimate of the range of values. Team is currently working to implement final versions of these models, so this range is going to narrow, and I'll talk about why AmeriFlux data is so important to helping us narrow the range in just a moment. And then you can also get annual ET summaries and cumulative time series for each year through this. Again, with just a few clicks of the mouse. The reason I picked this field to highlight in this example is that this is a field in Grand Valley, Colorado, where there was a incentive-driven water conservation program. This grower participated in that. And you can see the difference between 2016 and 2019, where they were up around 34, 36, 38 inches per year versus 2017, where they were enrolled in the program for the entire year, and ET dropped substantially. And then again in 2018, when they were enrolled for part of the year. So this ability to quickly and easily measure the impacts of investment in water conservation, investments by growers, and advancing on farm water use efficiency is really important, I think, to scaling a variety of solutions for sustainable water management in the West. So some of the applications we're targeting through widely available ET data include development of improved and more realistic water budgets for basins across the West, expanding and operating incentive-driven conservation programs at scale, ensuring agricultural producers and water managers that have already made investments in water conservation and improving water use efficiency are getting credit and can easily document and assess the benefits of those past investments. And then looking at ways to reduce transaction costs for water trading programs, so those can be implemented at scale. And then finally, for individual fields, we know that ET data can be really valuable as an input into irrigation scheduling and even for actually nutrient and fertilizer management applications. So making this data easily accessible and integratable with farm and ranch management software is a really important application of OpenET. So in addition to making the data easily available, it's really important that the user community has confidence in the data, understands the accuracy, and the accuracy is documented to be sufficient for use by farmers, managers in the private and public sector, and at the local, state, and federal level, and that it's actually being used operationally to support a variety of sustainable resource management practices at scales that are much larger than is currently possible. OpenET is taking an ensemble approach. So currently we're using 6 well-established models that have either been used operationally by a state or federal agency or are rapidly advancing towards operational use. This has actually in the past, in some ways, been a barrier to more widespread operational use, and that there are these different methods and practitioners have to decide which method do I use, what are the differences, what are the trade-offs. By putting them all together on one place, it's much easier to provide those comparisons and also to allow the community to work together to produce this single ensemble value that represents kind of a consensus view of the best possible estimate we can produce. Today, I'm taking advantages of the strengths of these different approaches. OpenET uses all publicly available data, satellite data from, I'll talk about those satellite inputs in just a moment, publicly available meteorological data sets, field boundary data sets, and other ancillary data layers. Similar to what Patty's doing, everything is running on Earth Engine. Data comes into Earth Engine. We run all the models there. That's allowed the teams to collaborate to improve the consistency of the inputs that are used to drive these different approaches. The raster data products and the summaries from the individual fields are stored on Earth Engine in a geodatabase and distributed both via the user interface, the UI that I quickly ran through, as well as through an API. And the API is there because we know that for a number of applications, ET data is most valuable when it's combined with other information sources. So we want to be sure that data can be automatically and easily retrieved for integration into irrigation management, scheduling applications, farm and ranch management applications, water data information systems operated by local, state, and federal agencies, and then also water trading and water accounting platforms that are currently being developed across the West. OpenET uses data from a constellation of satellites. That said, Landsat's really the workhorse here. The concurrent measurements and the vSphere and thermal infrared are really important for most of the approaches at the heart of OpenET. So that 30-meter, roughly quarter acre per pixel resolution overpass every 18-16 days makes Landsat just invaluable for this type of field scale ET mapping. We're also pulling in data from the Terra and Aqua satellites, SUMI NPP, GOES, and then the European Space Agency Sentinel-2A and 2B missions. OpenET has been user-driven from the outset. We have close to a dozen use cases across the West, spanning groundwater management, irrigation, scheduling and crop management, various regulatory compliance measures, watershed management and water trading use cases. Obviously, we can't cover every possible application, but I think this has been a really good representative set. In addition, we have developed working groups, actually with now over 100 members from the agricultural sector, local, state, and federal water managers, agritech startups, conservation groups, agriculture engineering consulting groups. So having this input from the community has been really valuable in thinking about how we build OpenET, how we design the API, how we design custom reporting tools to make sure that the information is both easily accessible and can be directly used for a wide range of operational water management applications. From the user community, we have developed user requirements. We've gotten requirements for spatial resolution, temporal resolution, data latency. But what I want to focus on today are these requirements for minimum and optimum accuracy. These are good aggressive targets. We think we can definitely hit the minimum accuracy targets. We're going to try to come as close as we can to the optimal accuracy targets. But without data from AmeriFlux, we really wouldn't even know where to start. So having the data from AmeriFlux makes it possible for us to characterize accuracy from all these different approaches and assess the accuracy for individual crop types, land cover types, regions, and seasons. From the intercomparison study that we're currently conducting, we will then identify the best performing approaches and the approaches that meet these requirements, and then calculate the ensemble value from the different approaches that are performing well, for each land cover type, crop type, season, and region. I think the intercomparison and accuracy assessment we're doing as part of OpenET is the largest intercomparison done to date for remotely sensed ET data. We're using information from Flux towers. This is really central to the effort we're undertaking right now. Also bringing in publicly available groundwater pumping records, in part because that can be a compelling comparison for agricultural partners. And then at larger scale, looking at water balances for well-characterized basins from USGS studies across the West. We've evaluated data from 198 AmeriFlux sites. Of those, 157 had sufficient data to assess the energy balance closure. These are some of the sites we looked at and used. We set a criteria for an average daily energy balance closure ratio of 0.75 for the growing season and 0.6 for the winter, and set a maximum of 5 missing days per month. There's a couple of sites where that was the only observation we had for a particular crop type or in a region, so we've relaxed that a little bit. But from almost all sites, we've stuck to that threshold of a maximum of 5 missing days per month. In total, we had 87 sites pass those filters. We went ahead and performed energy balance closure with an energy balance ratio approach. And we also brought in for agricultural sites, an additional set of data records from 30 Flux towers from sites across the West from partners of USDA, Cooperative Extension, Bureau of Reclamation, and other university partners. For each site, by the way, I want to acknowledge John Volk, Justin Huntington, and the team at DRI, who worked with Carlos Wang, who's with me at NASA and CSUMB, and is now with Dennis Baldacchi at UC Berkeley. They just did a heroic job going through all of these sites, looking at wind roses, checking to ensure that the grids we used to extract the satellite data were representative and homogeneous, running the dynamic half-hourly footprint analysis following the Clunadal approach for every single field, and then checking to make sure that there weren't meaningful differences between the dynamic flux footprint and the static gridded footprints we were using. And for some sites, we've been extracting data using both approaches for the comparison. For every site, we then extract the data from all the models, daily and monthly time steps for comparison. And it's been really a fantastic resource. So this allows us to see how different approaches, different models are performing. We have enough sites that we can release half to the teams for an initial evaluation. For many of the models, this is the first time they've been run in a fully automated framework at the scale of the Western US. So we used half the sites for an initial phase 1 comparison so the teams could conduct diagnostics and look for any indicators of issues with this initial implementation. The other half are now being held back for a round 2 blind intercomparison that will be conducted here a little bit later this winter. So it allows us to evaluate the models, see how both individual models are doing, how they fall within the range between unclosed and closed data records from the Flux towers, and then also how is the ensemble as a whole doing, and is it performing as well or better than any individual approach. For some sites, we're seeing really strong performance. This might be possibly one of the sites that Patty worked on there, Twitchell Island there in the Delta, Rice site. Other sites, we can see some models really aren't doing well, and that's really valuable. So we can identify the subset of models that are going to perform well for particular land cover types. And then in some cases, most of the models are doing well, and we might see one that's an outlier. So the teams, again, are taking this opportunity to perform final adjustments to the processing of inputs, implementation of the models before we produce this final comparison. And we are really excited to be able to release this operational system for the Western US next year because it's implemented on Earth Engine. We know that we'll also be able to easily scale it. Well, not easily, but in terms of the computation, we have the infrastructure to scale it across the US and even potentially internationally to other agricultural areas around the world. So a couple of observations and thoughts from the OpenET team. First, as I said before, those data sets from AmeriFlux have been just essential to our ability to develop this type of operational application for evapotranspiration data across the Western US. Having more consistent, regular, and frequent updates of the recently assimilated data would be even more valuable for these types of operational uses. So I could imagine that once we have the system, we'd really like to do at least annual, even possibly seasonal assessments to ensure that there's no drift in any of the satellite data products, something isn't going haywire. That ability to take advantage of the existing Flux towers over agricultural sites would be really, really valuable, and also for other land covered types. Additional and consistent information on land cover, crop type, and irrigation type. Any information on the irrigation type and configuration would also be valuable, especially if that's included in the metadata and standard ways. The addition of data sets,
Or it's just 1 minute left.
on irrigation measurements and any data collection on even irrigation frequency. If we can get irrigation data, that would also be really valuable as a diagnostic. And then finally, for this type of operational system, the ability to retrieve data in bulk for all sites and even to do subsetting via metadata would be really valuable. I'll stop there. A couple of other recommendations for the team. Also collected questions. I'm happy to share those with anyone that's interested. These are the types of questions we had to work through. And I'll just stop there and say, planning to go live in 2021. Thank you. We've done just enough work setting up Flux towers here in the Central Coast and Central Valley that I know how challenging it is to do the deployments and maintenance in production agriculture. So extremely grateful to everyone who's worked on the collection of this data and worked hard to make it available through AmeriFlux. So with that, I'll stop and say thanks so much. Happy to answer a question or two if there's time. I know we're running late, so also happy to answer questions in the chat.
Sure. Thank you very much, Forrest. Really appreciate your insight in this incredible new product. I hope that we can pull it a couple degrees further to the east. I wonder if there's anybody who has a quick question.
Yeah, we are working on that. So that's next on the list. The Western US has been plenty challenging initially.
Sure.
Yeah. I can't see the chat. So Ben, if you would read.
Yeah, sure. Some very affirming words from Anchor to share the model evaluations with the Flux Tower PI. So to make sure that the communication is two ways, I guess is the encouragement there.
Yeah, we're working on pulling all this together for publications, and we'll be sharing results back with the community for sure. I guess just in closing, I'll say the ability to work together as a community is really powerful. And I think getting out of competition is really important to a point, but once we get to a certain point, as we start to think about operational applications, developing funding models that really encourage and facilitate collaboration, I think can accelerate progress on taking our science and making it useful for operational water management. And we know we've got critical challenges we've got to solve, and data-driven approaches are at the heart of many low-cost solutions.
Yeah,
Stop
very
there and
good.
say thanks so much. Really appreciate the invitation and chance to talk with you today. Thank you.
Sure. Thank you again, Forrest. So our next speaker is Kim Novick. Kim, I think you're there and ready. Kim is coming to us from the School of Public and Environmental Affairs at Indiana University, talking about leveraging flux towers to inform land-based climate mitigation and adaptation strategies, emerging opportunities in the Midwestern US. Go ahead,
Okay.
Kim.
Well, I'm grateful for the opportunity to join this session. I billed myself a little poorly as I was making the talk. I realized this really should have been Eastern US and not Midwestern US. I also really want to thank the co-authors listed here. Kyle Hemis recently sort of corralled us to write a paper that he led, which I'll tell you a little bit about in a minute. But the process of working on that collaboration really sort of pushed my thinking on the topic. So I wanted to make sure to acknowledge their contributions. Okay, so I'm assuming that many of you are familiar with this figure. If you're not, this is a time series of different model projections for the global land carbon sink going from 1850 out till the end of this century. And the whole point of this figure is that there's a lot of model divergence near the end of the 21st century, and thus we need measurements of NEE in order to build better models so we know what CO2 concentrations will be like in the future, so we know what to expect from climate change, right? Many people have been starting in our field, have been starting talks with this figure, for going on 15 years now. And I just want to propose that maybe we've got a new figure that we'll begin to see at the start of some of our talks. Perhaps you haven't seen this one yet. This is from Fargione et al., 2018. I don't know this person, but I think they work for the Nature Conservancy. And this is the climate mitigation potential of a host of so-called natural climate solutions. So land cover and land management alterations designed to improve greenhouse gas balances over the land surface. And there's a lot to unpack in this figure, including the dependence of many of them on the price of carbon. But the main thing that I want you to look at today is the size of these error bars, which for some of these strategies is really, really wide, right? The coefficient of variation in terms of our uncertainty in these climate mitigation potentials is really large. And also please keep in mind that often these estimates are formulated using only long-term soil carbon studies, right? And so they don't incorporate a lot of the feedbacks that we know about, right? But that will be missing from that sort of data, okay? And public and private initiatives to promote these so-called natural climate solutions have a lot of momentum and a lot of money. Maybe you've heard of the Trillion Trees Initiative. I think it's kind of self-explanatory, but there's some other ones you might want to keep your eye on. One is called Indigo Carbon. It's part of Indigo Agriculture. This group has been raising hundreds of millions of dollars in venture capital to build systems to allow farmers and forest landowners to better access carbon trading markets. There's also a bill introduced by Indiana Senator Mike Braun in the Senate. It's also been introduced in the House, the Growing Climate Solutions Act of 2020, again, hoping to bring landowners and farmers closer to these carbon credit markets, okay? Now, we know that these natural climate solutions are not a panacea, right? Of course, the most important thing we need to do to avoid the worst impacts of climate change is reduce our fossil fuel emissions. But to keep warming below 1.5 or perhaps even 2 degrees C, we're going to need to also remove CO2 from the atmosphere. And natural climate solutions are a fairly palatable way to do that. There's been papers published recently that overstate this potential because they don't include many of the feedbacks and biophysical mechanisms that we know about, right? And our community has been pretty good about documenting, right? There's one more, okay. Attempts to overstate, let's say, the global climate mitigation potential of reforestation and afforestation. But I can tell you that those groups I showed you on the past slide, they're not reading these comments, right? They probably saw that first paper that came out. In any ways, it's a challenging messaging issue, right? Especially if we think of the case of reforestation or planting trees, right? We have learned for so long that planting trees is a good thing, right? It's how school children celebrate Arbor Day and Earth Day, right? And so then this messaging, well, no, planting trees not so great, is a confusing one, right? Which is one reason why I think these private and public initiatives have so much traction, okay? But I will also say that in some places, natural climate solutions are not a terrible idea. And now I'm thinking specifically about reforestation. I'm thinking specifically about the Eastern United States, which used to be dominated by forests. This is a map of the estimated area of virgin forest published in 1925 by the then chief of the US Forest Service. So this is based on land survey data. You know, by the early 20th century, most of those forests have gone. They have grown back a little bit, but certainly not to where they once were. So in places like South Central Indiana, right, if you want to grow a forest, you don't have to do anything. You just stop mowing your lawn, and in 20 years, you'll have something approximating a forest. Your neighbors might complain in the meanwhile, but nonetheless. All right, so how can the AmeriFlux community help reduce uncertainty about the potential of natural climate solutions, right? Where is this particular strategy a good idea? Where is it a bad idea, right? How can we narrow those error bars on that Fargione graph? And so the first thing I'm going to suggest is that you go to Kyle and Ben's breakout session on Thursday, which is dedicated to the topic. So as I said, Kyle recently submitted a paper, The Role of Ecosystem Scale Flux Measurements in Assessing Natural Climate Solutions. So we'll have a chance for a discussion, right? You can answer this question in the breakout session on Thursday. I am double booked, unfortunately. I can promise you I'd much rather be in this breakout than where I will actually be. So that's step number one. Kyle's paper does a lot of things, but among other things, it seeks to identify a framework for understanding when flux towers, how we can use flux tower measurements to better constrain specific types of natural climate solutions, then also identifying those that may be better constrained with other approaches, right? So I'm sure that Kyle and Ben will tell you more about this figure and other figures in the paper on Thursday. And then I just wanted to offer a few examples of some related work that we're doing here in the Eastern US, and I'm going to start again with reforestation. We know, we know a lot about forests and the carbon cycle, right? We know that Eastern US forests are relatively strong carbon sinks, and that they offset a good fraction of our regional anthropogenic CO2 emissions, right? This isn't news. But a question that we are very much still answering is, how does carbon uptake vary along successional trajectories, right? If you decide to allow an area of land to become a forest again, right? How long until it's a strong carbon sink, and for how long will that sink persist? This is a question that I started working on as a graduate student at Duke University, where we had a series of 3 flux towers. I'll go ahead and put them up here. A grass field, a 25-year-old pine forest, and an 80-year-old hardwood forest that represented a typical chronosequence for the Southeast United States. And the expectation, the theory suggests that by the time a forest gets to be about 100 years old, it will be more or less carbon neutral, right? So if I can just boil a whole lot of work done by a lot of people into a few numbers, here is the annual NEP or NEE from these 8 years of measurements from these 3 towers, right? And here's the Odom hypothesis, and we can put our data on the Odom hypothesis. We can say, oh, it looks pretty good over here, right? But look at our 80-year-old hardwood forest, still a strong carbon sink, right? We can also add in AmeriFlux data. That's the beauty of the network, right? Because still just one chronosequence in one place doesn't tell us much. But here I pulled in flux towers from the Eastern United States, here color-coded by plant functional type. And we can see that the Duke Forest Tower was not unique, right? There's a lot of mature deciduous hardwood forests in the Eastern US that are still soaking a lot of carbon out of the atmosphere, right? So it's not so much maybe that Odom was wrong, but maybe the scale of his axis was a little bit off. I also want to mention that you can see a similar effort in Chris Goff's paper from a few years ago, which is flux towers in the entire Eastern United States. And I can tell you that I get asked to comment a lot about the carbon sequestration potential of forests in Indiana. And one thing I'm often asked, a comment to the press or to testify in the state legislature. And often I'm asked to talk about the answer to this question: how does it vary with stand age? And I often decline those requests. On the one hand, because they're often linked to issues about forest management and how our DNR manages their land, which I really don't want to get wrapped up in. But also the truth is, we don't have a lot of data, especially for deciduous hardwood forests in this time span. In Indiana, there is no intermediate pine stage. I don't know, right, what the NE is of a 40-year-old hardwood stand in Indiana. So we have some work to do here. I don't think the solution is a whole bunch more flux towers, maybe a few more, but maybe some clever approaches that bring in some information from remote sensing or machine learning as well. Okay. Biophysical impacts came up once or twice already, and so I just want to stress that it is important to consider those as well, right? How about changes in albedo or sensible latent heat flux? How does that affect surface temperature? We know that in boreal climates, forests tend to warm the surface, whereas in the tropics, forests tend to cool the surface. What about the temperate zone, right? It hasn't been clear, maybe perhaps until recently, reforestation affects the local energy balance and surface temperature. And then just because you can demonstrate an impact on surface temperature, does that translate to air temperature? So my lab group has been doing a series of studies over the past couple of years, trying to get at that question. We had paired grassland forest flux towers from 6 sites in the eastern United States. And here I pulled all the data together. And the take-home message here is that surface temperature during the growing season over a forest is substantially cooler than nearby grasslands. If we compare air temperature measured directly above the towers, there's not much to see, but that's not necessarily a fair comparison due to canopy effects on temperature profiles. So we looked for some estimates of air temperature that were a little bit less affected by the canopy, namely the aerodynamic temperature and the near surface air temperature extrapolated into the surface layer. We find that the cooling effect is still there, though not quite as impressive as it is for surface temperature. But nonetheless, if none of that, if that just went over your head, no problem. The punchline is forests keep us cool in the eastern United States, in addition to their carbon benefit. Am I out of time, Ben? 2 minutes? All right.
2 minutes.
Then I have one minute to say something about cover crops, which is another, I think, really low-hanging fruit. So if you look at the mitigation potentials for carbon prices that are kind of near what they actually are today, cover crops, right? That's actually the largest air mitigation potential. So it's something that we're hoping to learn more about in the eastern United States. Most estimates of the climate mitigation potential of cover crops come from just soil carbon data, long-term, resampled every 5 or 10 years. All right, and those data alone cannot tell us about the mechanisms, right, responsible for any gain in soil C, whether it's enhanced GPP or decreased outflow, right? Keeping in mind that most of the Corn Belt is underlain by these tile drain systems. And there was one paper that used a paired cover cropped and non-cover cropped field with AmeriFlux towers to look at it, and found that cover crops do not appear to alter NEE, right? So we have a lot of work to do even for this particular natural climate solution. And so we're trying to build an approach that leverages flux towers, UAVs, satellite data, and also some of these point scale soil measurements. So hopefully the funding agencies will agree that it's a good idea, and I can tell you more about that in a year or 2. Anyways, it's fun to, I always think it's fun to think about new applications for our work, and these natural climate solutions have a lot of traction and probably deserve more of our attention. Patty also did a great job, I thought, of highlighting some related opportunities out in California. So go to Kyle and Ben's breakout session to learn more. Thanks.
Thank you, Kim. Thank you for the presentation and shout outs. There's been one comment that came in from Dennis that his Walker Branch data has forests in your age gap, so you should investigate that and put it onto your graph. I don't know if anybody else has a quick question before we switch to a wrap up from the breakout sessions.
It's been a long day.
It's been a long day. Think about your low hanging fruit and how to go measure it.
Yeah.
let's be part of the solution. Yeah.
And I have to go pop into my class for just a minute, which is happening right now. But if you do have questions, I'll be around all day tomorrow, or you can email me.
Okay, thanks very much, Kim.
Okay.
Good. I think we're switching over to Josh to lead the discussion of reporting out from the breakout